In 1928, a young man with a detached, almost robotic demeanor stepped onto a stage in Germany. He spoke without emotion, reciting his work as if it were a technical manual. This was Paul Dirac. To his colleagues, he was the strangest man in the world, a physicist who spoke so little that they invented a unit called the Dirac, representing 1 word per hour. But the paper he presented that day would send shockwaves through the scientific community. Werner Heisenberg, a giant of quantum mechanics, called it the saddest chapter in modern physics. This was because Dirac had done the impossible. He had found a mathematical bridge between 2 worlds that refused to meet. By the late 1920s, physics was a house divided. On one floor, you had Albert Einstein's special relativity, which mastered the world of the very fast and the very large, linking space and time into a 4-dimensional fabric. On the other floor, you had Erwin Schrödinger's wave equation, the golden rule of the subatomic world. The problem was that they were incompatible. Schrödinger's math worked for slow electrons, but it failed for electrons moving near the speed of light. Because of this, science could not explain why gold is yellow or why mercury remains a liquid at room temperature. The math was incomplete, and the search for a relativistic quantum equation was becoming a nightmare for physicists. Before Dirac, others had tried to unite these 2 theories. Physicists Oscar Klein and Walter Gordon created an equation, but it had a fatal flaw. It predicted negative probabilities, mathematically suggesting a less than 0% chance of a particle existing. To Dirac, this was an insult to the universe. He believed that the laws of nature must be written in a language of absolute mathematical beauty. If the math produced nonsense like negative probability, it meant the equation was ugly and wrong. Dirac set out to find a solution that was not only accurate but aesthetically perfect. Dirac's obsession with elegance led him to a lonely path of discovery. While his peers were busy arguing over the physical interpretation of waves and particles, Dirac was essentially playing a mathematical game. He spent hours trying to find a way to take the square root of the relativistic energy equation without creating the messy second-order time derivatives that plagued his predecessors. He believed that if he could just find the right symbolic structure, the physics of the electron would reveal itself. He wasn't looking for a particle, he was looking for a pattern. Dirac's stroke of genius came from realizing that ordinary numbers were not enough to describe the electron's journey through space-time. He realized he needed to use Fourier-4 matrices, complex arrays of numbers that could handle the symmetry of space and time together. By linearizing the energy equation, he created the Dirac equation. It was a masterpiece. Suddenly, the spin of the electron, something that had been a mystery, emerged naturally from the math. It was the first time relativity and quantum mechanics shook hands. This unexpected emergence of spin was perhaps the most shocking part of his discovery. Until that moment, physicists treated spin as a separate, strange property that had to be added to equations by hand to make them fit observations. But in Dirac's math, spin wasn't an extra ingredient. It was a fundamental requirement of a relativistic universe. It proved that the electron wasn't just a point of mass, but a tiny magnet with its own internal clockwork. However, this beauty came with a terrifying side effect. The math insisted that for every positive energy state, there had to be a negative energy state. The sad chapter was just beginning.